Welcome to WebRTC Live. In WebRTC Live, we cover the latest technical topics and business use cases for WebRTC and live video. As always, this episode is brought to you by WebRTC.Ventures, leading integrators of WebRTC video into your custom application.
Welcome to WebRTC Live. I'm your host, Arin Sime, founder and CEO at WebRTC.Ventures. We're a custom design and development agency focused on building live video applications, and we're here to help you take your application live. Thank you for joining us live today on YouTube, LinkedIn, and Twitch. Welcome also to any of you watching a replay of today's event. For those of you with us live, you can ask questions throughout the stream by leaving a comment in whichever platform you're viewing this. Before we go to my guest, though, I'm going to start today with some sad news in the WebRTC community. Bernard Aboba passed away this month. Bernard was well known, as others have also written nicely about him online since his passing. He's well known as a key contributor to the WebRTC standard, worked for Microsoft for a long time around real-time communications. Bernard was a guest on WebRTC Live a couple of times in episodes 31 and 51, where we talked about the emergence of WebRTC's 1.0 standard, as well as what comes next in WebRTC. In the times I had the pleasure of speaking with Bernard and meeting him in person, it was always clear his deep knowledge and passion for WebRTC and real-time communications. So rest in peace, Bernard, and thanks for all of your contributions. And now in moving on to happier news, for today's episode, I'm here with Péter Megyesi, CEO of L7MP. We're going to talk about the complexities of running WebRTC media servers in Kubernetes environments. Thanks for joining me today, Péter.
Yeah, thanks for having me. It's a pleasure to be here.
That's a pleasure to have you here. And let's start with, for those who are not familiar already, perhaps, can you start with just a little definition of Kubernetes and why containerized applications are so important in modern DevOps practices?
Yeah, so Kubernetes by definition is a so-called container orchestrator. So again, there are two words in that, so containers and orchestrator, that we should get a little bit familiarized. So containers, as you mentioned, became one of the cornerstone of the whole DevOps movement around 10 years ago. So this company called Docker made this tool that made it very easy to build and package application into these so-called containers. These are standalone, things that you can just run anywhere where you set up a Docker host. So before that, you had a lot of problems of you build an executable locally, you passed on to the operation people, and then something was just not working, dependencies, here and there going on and off. And this solved this problem, packaging, the dependencies, every lib together with the executable, maybe even the runtime. So if you have a Java jar up, you also package the, the Java runtime environment together. So you don't have this problem. And then you can, on the same host, you can run them isolated from each other. So it was a really neat, technology to use that. And I think in the past, 10 years, most of the people just incepted that either for testing or probably at this point production as well. So nice. then came Kubernetes, because Docker was such a cool tool that everyone just started to using it, and everyone realized that it's very easy to build and run container on one server, but if you grow out that one server, running containers on multiple servers is really, really hard. So because then you have a lot of problems of which server that I want to run my container, how do they communicate with each other? How do external, users come to, talk to my applications? So then, this became this problem of container orchestration, which means that how do I organize, multiple servers, or we just call nodes, because they can be either physical or virtual, it doesn't really matter, to one so-called cluster. So group them together as just one giant, thing. And then just run these containers seamlessly, and this orchestrator, kind of solve these problems of placing, one certain container to, the place where it's best to run, or maybe just scaling them, if the load is, getting bigger and bigger. And then, solving these communication problems, both internal and external, and then maybe, solving storage problems as well. So that was the bundle of these container orchestrating tools. And then 10 years ago, that was actually a boom of these tools because, again, Docker became just so popular. I think Docker came out in like 2013-ish. And then by 2015, there were like, I don't know, at least 30 different container orchestrators just on the market because, everyone had this problem. And then Kubernetes kind of like emerged of, the one tool that just like beat all of the others, which was like really interesting to see back then. I think so. Kubernetes came out, well, originally the first commit came in like 2014. So like that was, last year it was 10 years ago, but then the 1.0 version, so like the GA version of, that people started to use was actually coming out just 10 years ago, so like 2015. And so the core of the code came from Google, which is also, like a very good story. So because containers were actually existing before Docker, it was just really hard to use them. So like you needed like a pilot exam, as I like to call it, to use this tool. But like, the folks at Google, they're really good at this. So, and they were using that before Google. They had a system called Borg. I don't know if you watched Star Trek, but it's a reference to most people. So it's a giant system that like orchestrated everything at Google. But it kind of became very bloated. I think it was written in C++, so like it was very heavy to touch. So a couple of engineers decided, like let's sit down and like rewrite this from scratch, actually, with all the knowledge that they got 10 years before then. And rewrite it in Go, a language also made by Google. And then that became Kubernetes. And the other interesting thing is that when the GA version came out, so 10 years ago, they also donated this code to the Linux Foundation. So they made it not just open source because, the source was available before that, but like giving away to this foundation. And then actually they made a sub foundation. It's very, very how we call it. So we have the Linux Foundation. That's now a very giant organization, but they have this sub foundation called the Cloud Native Computing Foundation, who handles the code of Kubernetes and now a lot of other projects related to this whole like cloud native ecosystem. So, and then this journey, started, and then a lot of the people actually give credit to CNCF, as a short, the Cloud Native Computing Foundation, that Kubernetes became so popular because they're very firm in that they wanted to make this tool very like vendor independent. So even though, like Google made this code at first, and they are still to this day the biggest contributor, but they were very, they made this rule so that, no one vendor can like suppress the whole project. And then it's kind of like very democratized, among all the big vendors. So, like a lot of other players now contributing a lot. For instance, Microsoft is one of the other biggest contributors. Red Hat, now maybe IBM as well. VMware was a very giant player in this field. So the whole industry just started to like incept these tools, and then they just left all the other tools. So they had a lot of other, like competitors again back then, like 8 to 10 years ago. Docker had their own orchestration tool, but it just like kind of died out. It was called Docker Swarm. People are still using it, but it's, like it remained very niche. And then again, Kubernetes just became a winner, and I can like firmly say that most of the container orchestration, like let's say 99.5% are Kubernetes today.
Yeah. So yes, so many things go back to, research projects at Google, whether we're talking about Kubernetes or WebRTC itself. Yeah. An interesting thing about containerization in Kubernetes, I mean, this was built more with like a standard website in mind, perhaps a standard web application than say WebRTC or the unique needs of real-time communication applications. And certainly when we talk about WebRTC, stun and turn servers remain one of the most asked about topics in WebRTC. You look at, I know the videos that we make, the stun and turn ones that just kind of explain that always are the most popular videos. I'm sure it's true for many others too, even nearly 15 years after the birth of WebRTC. So what is it that makes like stun and turn so complex to consider in real-time applications, and how does that complicate the way you would deploy containers with Kubernetes?
Yeah, so I think one of the interesting choices that the WebRTC designer made, who again was coming from Google. So again, Google is a big player here. Is that they try to mimic this sort of like networking behavior of like first Voice over IP, which was mimicking like, let's say, telecom systems, so like like mobile carriers, how the network working there. And it's just this interesting fact that whenever, well, first of all, it's a peer-to-peer protocol, so you always like talking to one peer to another and back. So even though like if there is a multi-party like video conference, you always talk to one peer, and then you can have multiple peers, but peers having peer-to-peer connections, and that's it. And so and then how it works is just these peers choose random UDP ports, and via signaling, I will ask my peer that, okay, here's my random port, try to connect me here. And that's just not how the current like web or Kubernetes or like any other cloud thing, it's just supposed to work. So Kubernetes itself and all the other like, let's say, major like cloud provider were made mostly for like, let's say, like HTTP, so like web traffic, which is like inherently, first of all, stateless, and it's just like a query response. So it's just very fast. Like I ask one query, I get an answer. Okay, I ask another query, it maybe goes to another server, right? But I get the same response. So that's the kind of the idea, and also Kubernetes was built for this, and most of the use cases there were like built for this, like HTTP and web. So that's just that.
Excellent. Yeah, I think you have a few slides, so maybe you can walk through and show us a little bit more about how those connections work.
Let me just, so this is, when I was talking about that, whenever we talk about WebRTC, again, it's a peer-to-peer protocol. It doesn't really matter whether, like there are two peers that both like humans using their browsers, or like maybe just one human user talking to a so-called media server. Essentially, the flow is the same because the same protocol, right? WebRTC. So again, what happens is that both of these peers chooses a random UDP port, because there is no like, like user authentication and anything built into like at least this part of the communication. It's just you purely say that, okay, I know my peer because she or he could, connect to my random UDP port. But how can I send this to my peer? There's this thing called the signaling server in the WebRTC architecture, and while WebRTC itself does not define how the signaling works, it just only defines like how should you describe your signals, which is this thing called SDP. It's a very ugly like text like descriptor that you can see. It's just a snapshot, so you will actually get way more text than this, but I don't know. Before I saw this, I thought that XMLs are ugly, but now I know that SDP is probably way worse. But anyway, it's just machines can translate it, and then that's it. And somewhere in that you will see these random UDP ports. And then first of all, you upload this to the signaling server somehow. Usually today it's like HTTP or WebSocket, or like again going back to the web world, it's one of these protocols. And then you somehow download it, the SDP of your peer, right? So then you know where to connect. And then you just try the connection, like, okay, I see this, like random port, and I will try to connect. And my peer is also will try to connect to me, to my random UDP port. So that's a fundamental, like peer connection flow. And then obviously the giant problem with this whole thing is that, this will only work if, both peers are on the public internet, right? There's no way it works, like, again, I'm sitting home and you're probably sitting home. We are, behind some, residential router with network address translation. It just kills the whole flow, right? So like, although media servers can have public IPs, and most of the time, I think you can confirm that that's the case of today deployment of like, you will most of the time will deploy your media server to have a public IP so that this flow is easier. Right now, when we talk about cloud and then again home routers, it's a little bit more like this. So like you have you only have a private IP, and then somewhere else you have a public IP, right? So like you could imagine this scenario, and that's where the whole STUM protocols come to the picture. So STUN is just a server sitting somewhere on the internet. You can use public STUN servers. So like Google has public STUN servers and pretty popular to use it. And then now maybe Cloudflare has their own. So you can also use it as an alternative. But basically STUN servers are, I like to call them as like a glorified what is my IP servers. So like you send a STUN packet and you will get back your public IP. But not just that, it's glorified because what it will happen is that your home router will actually leave that UDP port open. Notice that the UDP port is different because you do network address translation, but they know these protocols, these like, simple routers, because STUN has been out like, I don't know, 30 years or so. So every, commercial router speaks this. So when they see a STUN packet, they will leave that port open, right? So then you will send these information in your SDP to the signaling server so that you can try to connect to these kind of like, we call it the STUN reflexive IP and port, to see whether I can connect, and hopefully that router, that NAT device, will forward my traffic to my peer's random UDP port. That's the idea. And that's actually working fine, I think. I haven't checked this now, but probably we are using STUN right now to talk to StreamYard, right?
Right. I think so.
Yeah. So it's a very easy, tool, and it works neat. And again, STUN servers do not forward the traffic of audio and video. They just use to get this basically public IPs and ports, and then and then basically the routers will leave those ports open. Now the biggest problem is when I go forward is that again, that works with this kind of like residential routers that you get from your ISP, but there's no way it works in like enterprise routers, or like usually not even working for like 4 or 5G like mobile packet stuff, because it's a huge security risk if you think about it. Like just a rogue element in the network starts to send out a lot of like stem packets that will like overflow your NAT device, and then people from anywhere from the internet can connect back to you. So that's a very bad idea. So almost like always when you talk about enterprise customer, it will not work. And on the other side of the equation, while STUN might work, it actually may or may not work. Certain cloud providers also forbid this. But like some simple cloud VMs will actually be able to do this. But like when you put those kind of like Kubernetes networking, again, I mentioned that, in Kubernetes, we have nodes. Those usually have private IPs. And then we also have like containers. They also have like their own virtual network. So many layers of NAT that, sometimes, surprisingly, sometimes still STUN can go through, but really you cannot rely on this. So you need something else to solve this problem. Yeah, so let me just jog through the slides. Maybe it's a bit too like deep on how Kubernetes is actually working. So again, in Kubernetes you have nodes. Nodes usually have a private IP, and they may or may not have a public IP as well. But those are just also netted public IPs. So the address that the nodes will see are basically always private, almost always. And then again, those containers, or actually in Kubernetes terms we call them pods. Pods is just you can put multiple containers in one pod, but usually they are almost interchangeable in this naming convention. They have their own flat IP network that they communicate inside the Kubernetes network. And then in Kubernetes, you kind of have this so-called like service abstraction that there is another separate like virtual network that usually you use to talk to your pods inside the cluster, because it has also a built-in DNS, and then it can also load balance your traffic when your pods communicating with each other using another tool called kubeproxy. That's a built-in tool. It's basically some fancy IP tables magic happening in the background, but again, it's just like additional network layers, virtual networks, nets on top. And if that's not enough, like when you do external communication, what you get usually is that you get a so-called public load balancer from your cloud provider, and that will do some sort of like load balancing and some other net layers involved. So usually I like to, like say that whenever you do this kind of communication from the outside, so you as a user into like a Kubernetes pod, you will probably go through one or two like source net layer, like your IP actually will change at least like twice or maybe once, but probably even twice. And then the destination layers will also change at least once, but also twice. So again, no way that Stun goes through all this. But like sometimes it actually surprises us that, for some reasons, sometimes it can go through. But again, we like to say that you cannot really rely on Stun because of this, because
it's not repeatable or predictable.
Yeah, exactly. And
every
and
time
again,
we reconnect with each other, it's going to be over some different path in the network.
Yeah. So that's the kind of like the idea. So then again, how people are solving this problem is like usually that there's one way that we do not really like to use, or at least I don't like to use. And one of them is a thing called that is working in Docker itself and then Kubernetes as well, which is a thing called host networking. So what it means is that you can actually start a pod or a container that it inherits the IP address of the node itself and does not participate in this kind of like Kubernetes pod virtual network layer. So like you're kind of like using the node for this. And then again, because if you have a simple like public IP that points to one specific node, then it's a time that Stun might go through. So because of this, a lot of people are using it, but I have to admit that in Kubernetes terminology, this is just such a huge anti-pattern that I never recommend it to use. Mostly because of if you use the host network, it means that you can only run one of the same pods. So in case of media servers, you will be only able to run one media server per node, because otherwise you will get these port collisions, right? So this will just make normal Kubernetes processes like very, very hard. Even just like upgrade your pods, because first you have to kill your pods and then start a new one. Running new nodes will be very, very complicated. So this again have a lot of scaling issues. So because if you need more pods because you have a large load, you essentially need more nodes, and then scaling the nodes is extremely hard compared to like just killing pods. So that's always a thing, and it has a lot of like compromised security. So some of the security features that Kubernetes gives you will not be guaranteed if your pod's running in host networking mode, and that's why like most of the enterprise customers that we work with, it just flat out blocks this option. So like you cannot run in an enterprise cluster a pod with host networking mode. That's just
defeat the whole point of you going with Kubernetes when you're trying to scale with high security. And so we don't want to go this way.
And then, well, even if you do it, you kind of have to face that issue that, okay, maybe your peer can connect to you using this, like Stun and this node public IPs, but how can you connect to a, like an enterprise customer who are behind a restricted firewall? And then, there is no way to do that other than using a turn server. So even if you do this, again, you will need a turn server anyway. You will always need a turn server, right? For this kind of like users behind restricted firewalls and then just like complicated net devices. So that's kind of the idea. We like to say that if you're in Kubernetes and you want to use the normal like pod networking so that you can use all the feature that Kubernetes provides you, there is no other option than to use a turn server. So turn is different than Stun. Turn is basically a relay. So you as a user can connect to a turn server, and then the media server can connect to the same turn server, let's say. And then, it can just hook your traffic together. So that's kind of the idea. That's the basic idea. You can use different, type of turn, but that's the most popular because, that's easiest to basically implement. And then basically what you can do is just, well, there are a lot of turn service providers, so you can just like get a subscription from them. I listed a couple of them here that I know about. So these are like tools that you can use. Very easy to set up. Turn is a protocol, so just like Stun. So again, setting up this into your WebRTC infrastructure is certainly very, very easy. But it comes with other things. So what it does, it adds a lot of latency, and then it can be a lot of latency if you are located in a region where that certain provider does not have turn servers, right? So if currently I'm in Budapest, if I want to talk to my friend at Budapest, I don't want to like send my traffic to US East, right? Just because my turn server provider is there. So you kind of have this trade-off that you have to make. And the other thing is that you will pay for this. So, and then usually how much you pay is based on the traffic, because we're talking about WebRTC. A lot of the WebRTC use cases are video-based, so meaning that that's a lot of traffic, right? So you will pay at the cost of like per gigabyte. That can add up, and that can add up very, very fast. So you might want to be very, very careful to how to use it. But a good advice is that if you're starting with this kind of architecture, like even just setting up this external turn server are really, really easy. So you can always set up, and because it's a like an IETF protocol, right? You can always change it to something else.
Yeah.
So
and as we talk about kind of the commercial options for turn servers, I'll give a plug here to our friend Dan Jenkins' service, iceperf.com, that helps you look at and compare some of those different turn networks. So
exactly. So yeah. If you go to iceperf.com, you can find a good like summary of all these providers. You can find I think like performance comparisons, pricing comparisons. So anything you need, just go to iceperf.com. I will put this on my slides if I next time I will talk about this, because we are also on iceperf.com, I have to admit, because the other like alternative, let's say, that comes to your mind is that there are a handful of open source turn servers out there on GitHub, but you can just run your own, and then you're good to go. You don't necessarily have to pay for like all this traffic, but there's a huge like bot out there. It's just really heavy to run this, because you have to consider a lot of things when you're talking about turns. So first of all, well, you have to maintain it, this kind of like, it's another dependency of your whole architecture. And you kind of have to make it so that, it can handle all the bandwidth. And then again, maybe you're not paying for the bandwidth, but you have to be very careful of like, how do you load balance between all these turn servers so that, it can handle all the traffic. And again, it's video, so it's a lot of traffic, so that, you have a smooth experience. Like, again, I mentioned that you have to make sure that your hosted turn provider has a region deployed there. If you're having a global, I don't know, like a global service that you're providing to your user, you kind of have to like do a global turn server deployment, which is also very hard to do. So, and then there are a lot of security concerns about turn. Security concern. You have to use it very carefully if you're setting up for yourself, because you never want to, use it as a attack surface to your own infrastructure. So it's very, very, I would say it's very hard to set up a, scalable, secure turn service. It's not a surprise that, there are only a handful of hosted providers, right? Because of this.
Right, exactly.
So, and then, like finally, what we probably wanted to talk about today is that, okay, but we have another kind of like option. Can I run this turn server inside the Kubernetes cluster, like next to my media server? Because, that would be like quite efficient, right? Because then, I make sure it's close to each other. Then I can use Kubernetes to orchestrate my turn servers, right? That would be a good thing to do. And then the answer is that, yes, And then that's why we built our project, which is on GitHub. It's called Stunner, which is basically, Stunner is a stun and turn server, but like mostly turn, to be honest, purposefully built for Kubernetes. So Stunner was designed to run in Kubernetes environment, although I think you can run it without Kubernetes. At least my colleague can run it. I don't know anyone who are running it outside of Kubernetes because it was made for it. And then you can run it as a regular pod. You can do a lot of things, just as if you're used to Kubernetes. It's actually written in Go. Most of the things related to Kubernetes are written in Go. It's based on the Pion Turn library, which is like, very popular these days. The whole Pion libs about WebRTC. And again, it's just very native to, like for Kubernetes people. So if you know Kubernetes using Stunner, I would say it's very, very, very efficient. So it's very easy to install because it's just a couple of YAML files. It's very easy to manage. You can scale it horizontally. So in Kubernetes, there is this thing called a horizontal pod autoscaler, which whenever you see there is a high like CPU load on your pods, it will just start a new one. And then again, those cloud load balancers will make sure that the turn traffic will be load balanced among your Stunner containers. And then the other very, very good thing that we get a lot of like feedback for this is that this way you don't have to expose like thousands of UDP ports to your infrastructure, which is kind of like you have to do when you talk about WebRTC, right? Because they can open any random port. So sometimes you face issues, or at least our like clients say that it's so good that they don't have to open like 10,000 ports, like setting this up in a firewall. You will only have to expose like a couple of turn ports, and just a couple because usually turn is used in UDP, TCP may or may not, and with TCP TLS. So you will only need like 3 ports to do this. And then everything in Kubernetes is good to go, like monitoring, GitOps, like certificate management. It's just, there are these cool tools that around Kubernetes, again, because it's open source and it's been out there for 10 years, you can find anything. It will just be able to use. One thing that I have to mention is that, putting every traffic into a turn tunnel, essentially, which is like basically a tunneling protocol, will like give you a lot of like extra CPU loads. So you kind of have to, calculate with this. So like if you're using Stunner very heavily, then, it can have high CPU loads, just as high as your, like standard media server SFU, for instance. But then again, you can just horizontally scale this and then it will work. No problem. So, yeah.
So what percentage of traffic in this sort of setup goes through turn when you're using Stunner?
Yeah. So in this setup, I would say that when the user wants to connect to the media server inside Kubernetes, that's 100%, to be honest. So because of because that media server is in this like digged away very heavily into this like cloud nets and stuff, that we will always use turn, at least in like that's how we recommend this. And then the interesting fact is that the media server can connect back to the user with regular stun. So again, if you're just home with behind a regular like residential router, it will work. So that's always an option. So you don't have to go through Stunner there. But again, if your user is behind a restricted firewall, it can open a turn connection to Stunner. Usually, like maybe UDP is blocked, but usually using like the TLS version of turn at port 443, because sometimes firewalls thinks that it's HTTPS because it's TLS, so they don't necessarily look into it. And that's how all the other turn server works, to be honest. So then it can still connect to Stunner, and then then Stunner will do this kind of like hook up the traffic together. So that's the whole idea.
Makes sense. And so you mentioned monitoring those turn servers then and being able to horizontally scale them. What key metrics do you look at to know if the turn servers need to be scaled? What do you configure around that? Is it primarily the CPU load, or are there other factors?
Yeah, that's a very good question. So we use primarily the CPU because that's built into Kubernetes. So like running this thing called horizontal pod autoscaler is very easy if you're using CPU or memory. So you rely on on these two metrics because it's very easy to do the integration. Kubernetes sees it by default. And because again, turn servers, so like Stunner itself as well, is CPU heavy. So it is very easy to set up a CPU based autoscaler. Other than that, in this whole like Kubernetes era, there is this other tool, which is also like part of the CNCF. It's called Prometheus. That's like the de facto monitoring tool in this cloud native environments. We do support, obviously, Prometheus. So you can see a lot of metrics of like connected users, connected allocations, and so on. And then Kubernetes has a way to auto scale on these metrics, although it's kind of like more complex to set up. So we see a few implementations out there, to using this called custom metrics. That's the term that you want to look for in Kubernetes, custom metric auto scaling. But like, again, regular CPU, which is, to be honest, does the job.
Yeah. And on the other side of Stunner, once the connection is established, you could work with any open source media server, basically, in this configuration. You
Exactly.
mentioned.
So because this whole thing is like a standard, like Stunner and Turn again, IETF standard, and then WebRTC now also standard. You can just put any media servers, and we do have, if you hit our documentation page, we do like have a lot of examples, including all the popular media servers like like Janus or Media Soup or LiveKit as well, Jitsi. So like we do support like all of this because it's not like we support this, the protocol itself like give this support. So I can show you a quick demo if that's okay.
Yeah, let's do that.
So again, here's my terminal, which is just a regular like I am connecting to a regular like Amazon cluster. So that's like EKS, Elastic Kubernetes Service. Running free nodes here. And then here I have one pod, which is again pod and containers, almost the same in this terminology. It's a tool called Neko. I purposefully wanted to run this demo, not to run a classic media servers like the one that mentioned, just so that people will not look into this of like, oh, why am I using LiveKit? Why am I not using Jitsi? Well, I use something completely different. So this is just a cool open source project. It's called Neko. There is no like company behind it. It's just basically one guy, this guy called Miroslav behind it. And then what it is basically it can run you a browser inside a Docker container and then stream that browser to your browser using WebRTC, right? So it's a pretty weird setup. And then, like multiple people can join to the same session. So you can watch the same stream, right? And then you can send messages and stuff. But basically it's a kind of like weird using WebRTC, but it's still WebRTC, again, the same stack. I think because the server itself is with Go, it also uses the Pion libraries as well to do this kind of WebRTC. But it's a fun project that I like to demo because of this. And then how it works, again, because it's standard Kubernetes, it's just a couple of YAML files, right? I have a deployment, which will run me one Neko pod. That's like I can choose multiple, but again, one is enough now. And I will run just Firefox because sometimes other browser, especially Chrome, needs a lot of like other setups, and that's it. And how I do this is just like I set up passwords and stuff. And then there is this point, and that's happening all the WebRTC applications, that you have to give this so-called ICE config. ICE is just a process that does this gathering of the called candidates of like what should I send in my SDP descriptor, so my peer can connect to where. So I will send my so-called host candidate. That's my own IP and port. I can send these stun candidates. That's the one that I got back from stun. And I can send so-called relay candidates, which you should connect to a turn server, and then try to connect me via turn server. So that's basically it. Right now, I'm having Neko deployed only with a stun setup. So again, that's Google public stun server, and the demo that I will show you is that okay, this won't work, obviously. And the rest is just, like standard Kubernetes thing. Again, we have a service that kind of we always have in Kubernetes. And again, in Kubernetes, we have this so-called ingress, which is just basically an HTTP endpoint to your cluster. So like you can say I have a domain name setup that routes to an Nginx somewhere inside the cluster, and that Nginx will like send this HTTP traffic, but that's just for the signaling and also for the front end that I will use. So if I well, let's say this is my domain name, I have to copy this and go here. If I just type it here, I see this is just the front end of Neko, but as soon as I want to log in with admin, I will see that it tries to log in and then get this WebRTC connection, like the peer connection that we were talking about, but it just won't work. And then Chrome kind of has this like Chrome WebRTC. If I find this, sorry, not this, WebRTC internals. That's a very useful page when you are doing this. Well, I can see how I'm connected to StreamYard, but now because it's also WebRTC. But now I want to use this Neko page, and then we kind of see that we exchange this candidates. These are like local candidates. Maybe I need to like just restart this. I'm sorry, because sometimes it will fail and then it does not appear. But the thing is that here is the remote candidate, and then even though I see where my where this media server is, I cannot connect it, right? Because it's just done. If I do kubectl logs Neko, I will see this whole process like failing probably in the logs somewhere here. Even though like if I go up here somewhere at the beginning, maybe just having too much logs at this point, but somewhere okay, it's too much log. Let me just write like sorry, maybe head -20. This stream will see. I'm not sure why, but the server itself will see it's a public IP somewhere. Okay, I cannot seem to find it, but it really doesn't matter.
Yeah.
At this point. But the point is, again, I got these stunned candidates. It's called this is the server reflexive candidates that it's somewhere here, and then I was just not able to connect this. Right. So then again, I just reconfigured this micropod. I have Stunner set up because it would take like only a few minutes, but I did not want it to wait this. The only configuration that I changed is that instead of using stun, let's just use like the turn server, which is it's actually pointing to like kubectl get pods -n stunner. Believe me that it will point here. There are a couple of stunner pods running here, three of them. The other one are just other parts of our control plane. But it is running here, and it has this domain name. And I say kubectl apply -f Neko, and this will just restart my pod. I mean, instead of restarting, actually running a new one, that's also something that that's the kind of like the Kubernetes way. You always get your container killed and and then having a new one, but that's actually no problem. So now I have to refresh this. As soon as I refresh the configuration, I'm able to join here. So like you can see that this is the what I wanted to see. And if I type in what is my IP, I should see some sort of like IP related to, well, it's German, I think, because this is because this particular browser is in like I think Frankfurt. If I'm Frankfurt in well in AWS. So one just final thing. If I type kubectl get nodes minus -wide, I will see the node public IPs, and then and then I should see like which node is that. It's a little bit like. Can you see this? Well, one of these was that, right? 2020. This node. So I actually know that this pod at this time running on this node with this public IP, right? Because that's how the traffic goes out. But then we were able to make this work. If I go back to WebRTC internals, maybe I go back to here. Oh, I think I just got back to the StreamYard. That's how like StreamYard is actually, I think, again working with Stun. But again, if I come back here, I should see this kind of like remote candidate, like setting up, like some sort of like internal IP addresses in Kubernetes. But there is no problem using the turn protocol and the relay candidate. I was able to, join to this WebRTC system, let's say. And again, the same does apply to any standard WebRTC video servers out there.
Excellent. Yeah, thank you for that demo, Peter. That's really helpful. It's like walking through the first part there where you can't connect and you just see the sort of the pulsing graphic on the NICO UI there. It's like the nightmare of every new WebRTC developer where they build their application. They're like, oh, it works locally, and I followed this, WebRTC in 5 steps, easy tutorial, and then they finally have to learn about, oh, so there's this thing called turn that I have to use. And now, worse when you're trying to do that at scale across the globe, across corporate networks, all of that sort of thing. So there's a tremendous amount of complexity here that the Stunner project helps with. So definitely appreciate all the information you've shared about that today. And one thing I want to make sure as we're getting into our last few minutes of the conversation here, but I want to make sure that I ask you, why do you call it Stunner when it's mainly about turn servers?
That's a very, very good question. So again, the whole magic in Kubernetes is actually happening with the turn protocol, not the stun protocol. And then we still have this name called Stunner. We should have called it probably Turner, but the whole idea is that again, like our company, again, we are located in Budapest, Hungary. We were colleagues at the local Technical University of Budapest. Most of us in the founder team having PhDs in telecommunications, and my colleague were doing like a research project for Ericsson for a very heavy telco use case. So like imagine like putting a complete telco core functionality into Kubernetes, and then they actually started to do this. And as some of the data plane, like traffic connections were not going through, and the reason was the same. It's just in a telco network there is only private IPs, and it's a so-called flat network. So you will see everyone else with their own IP, and then you can just connect to the random UDP port that they give you. But as soon as you put these functionalities into Kubernetes, behind a lot of nets, that was not working. So they needed to implement, like stun and turn into that process as well. And then, first they just started with stun, and that's why they called it Stunner. Turned out it's just not working, so they had to implement turn as well. So then it just became a turn server. And then what my colleague realized, and that's when we just founded the company, is that even though this is like a very heavy use case for telcos, it's all the same in the WebRTC world. It's a much more open world, like a lot of people using WebRTC and building up on it. So it would be a cool tool to just support the WebRTC developers.
Excellent. Well, and Stunner sounds more like it sounds almost like it could be a Star Trek reference itself, better than Turner would.
Yeah.
But and one last question from one of our viewers is unrelated specifically to Turn, but thinking more kind of curious your impressions on Kubernetes in general. Do you see a place for generative AI, for AI and automation around Kubernetes infrastructure and workload management? Do you see that coming in your work?
Yeah, absolutely. I mean, I just recently put out a blog post just to how to run, like, again, LiveKit and LiveKit agents. You're probably like familiar. They're doing fantastic work in this area as well. Yeah. Not just the media server itself is a very good one, but like AI agents is very easy to use and very easy to implement. And like Kubernetes is basically good for when you have this kind of like complex architectures. So if you just have like one monolithic service you want to put out on the internet, that's not necessarily the case when you want to use Kubernetes. But if you think about like these AI agents and WebRTC and a lot of other services that you want to put around it, like authentication, signaling, like turn again. And then, like databases, all the proxies and stuff. So it just builds up to a complex architecture that's really, really hard to build, I think, without Kubernetes. I mean, it's certainly possible, but if you think about, like how easy to add a new service, like a new AI agent container here and there, just plug it in, like run it, scale it. I think it's certainly a good way to move forward. And just one other thing with Kubernetes and AI, because like Kubernetes has been out there for 10 years. I think it's a very mature project, right? So again, most of the big companies and smaller one as well are using it for years now. So most of the actually like novelty that is put into Kubernetes is on the AI field, to be honest, of like, like how can you make it more, like natural to run this kind of like, AI tests, like maybe even training and inference. And, OpenAI is actually very famous about that they've been a big power user of Kubernetes. So as far as I know, all of the GPT-2, 3, and 4 models were solely trained on Kubernetes clusters while running in GPU nodes, right? So that's kind of, I think it's a very perfect intersection.
Excellent. All right. Well, thank you so much for all the time today, Peter, and really, really interesting presentation and excellent demonstration of the concepts. So appreciate it. How can our viewers learn more about L7MP and the Stunner project? Yeah,
it's just we have mainly free sources. Just hit our webpage at l7mp.io, or just find the Stunner GitHub page. Just type in Stunner, and it will just like l7mp/Stunner. Or come to our Discord server. We have that for communicating with users who have any questions. That's probably the perfect place to get started.
Perfect. Thank you again for your time and for joining me today, Peter.
Yeah, thank you for having me.
All right. Well, remember to stick around. I'll have Sahi joining me for an industry analysis segment in a moment, where we'll talk about AV1 in WebRTC. We almost go through an entire conversation without mentioning AI, which is pretty rare these days. But first, let me remind you that this video will be available on the WebRTC.Ventures YouTube channel, as well as on our blog at WebRTC.Ventures. Our next WebRTC Live episode will be on Wednesday, March 19th. It'll be the 100th episode of WebRTC Live, and so we'll have a discussion with some of our own experts from the team for this special episode. To find out more about our upcoming episodes, follow us on social media at WebRTC Ventures on Twitch, LinkedIn, YouTube, and join our email list at WebRTC.Ventures. Thanks, everyone, for joining us today. Let's make it live. Thanks for joining me today, Sahi. Let's talk about AV1. What's the state of the art and the state of compatibility in video encoding today?
Sure. So AV1 is a video codec that is optional in WebRTC and implemented across the browsers. If you think about video codecs in WebRTC, these are the tools that we use in order to encode and decode the video, or compress and decompress the video. So when we do this session now live, or when we do the session for recording purposes on WebRTC, we both send our video across the internet compressed. We do that also if you watch a YouTube video or anything else. We don't send uncompressed video. It's impossible to do that. The mandatory to implement codecs in WebRTC are VP8 and H.264. And then we had VP9 come in, and companies started adopting it over the years. And then came AV1. The main difference between AV1 and everything before that is that there is like a complete acceptance of the whole industry for this specific codec. With H.264 and VP8, you had different groups saying we want different camps in each side, saying we want this codec, we want that codec. H.264 because it's legacy and everyone supported that, and there were patents involved that people got money for using that codec, versus those that didn't want to use that on the VP8 side that said, well, we don't want to pay for patents. So there was a big fight there. We got two of them as mandatory to implement. Then Google came out with VP9, another royalty-free codec, placed that in WebRTC. We still got people not wanting that. And the reason was because this was Google. We don't like Google as a company. And the ecosystem didn't grow around VP9 as big as it should have. The other thing is that VP9 also competed with the HEVC, which is the successor of H.264, and again, a problem there. At some point, the industry got to a point where they said, let's open the alliance of open media. and put an AV1 codec in there. That's how they called it, and that codec is going to be royalty free. No, so you don't need to pay for the patents, and we're going to back that up as the whole industry. So you'll have there all the browser vendors, which are also all of the modern operating system vendors. You have the large cloud vendors, and in cloud I will also include Netflix and Amazon, so these two are there. Then you have vendors like Cisco in there, and chipset vendors like AMD, and I think NVIDIA is also there, I'm not sure. The only missing company there for some reason is Qualcomm. They do have patents on HEVC and H.264, by the way. But the end result is that everyone is in AV1, so AV1 is going to be with us for the coming years. Then the question is, when are we going to start seeing the adoption of AV1? Now, an adoption of a video codec requires multiple steps to it. We need the hardware to support it. AV1 takes more CPU than H.264 and VP8 and VP9. Why? Because it's more complex. It can compress a lot better. So we need better hardware. We need to wait until a lot of devices out there die off on us, and we stick to those that are new. Then there is hardware encoders and decoders. We want these, and we don't really have hardware encoding and decoding for AV1. We do, but not a lot and not enough, and not in most devices and chipsets. After we have that bit done over the specification that was finalized only 2 or 3 years ago, then you need to start having developers that will build their products on top of it. We had AV1 in WebRTC in Chrome for a few years now. Nobody really used that because you tried using it. It took up too much of the CPU of the device. And when you ask yourself, well, how do I even do this session that we have now of one-on-one call? And the answer is, you don't, it's impossible. Okay. Ever since then, the software codec that is being used for encoding and decoding AV1 has been optimized. And it has gone through phases of optimization, where today I think it has been said that it's like 17% or some other, not such a big number, above the CPU requirements of something like H.264,
Okay.
which is not that bad if you think about it.
Right. And the compression benefits you're getting are much larger for that
Yes.
extra CPU cost.
Yes.
Right.
And it comes with SVC, scalable video coding support, built into it already. And you now also have all of the RTP payloads and headers and stuff that you need in order to support that well, almost out of the box. So the only missing piece in a way is someone to take all that and implement it. And yes, Google Meet supports AV1 for half a year or a year now already. It's something that we've reported inside WebRTC Insights long ago. What was interesting is what happened 2 months ago when Jitsi announced that from now on, Jitsi Meet prefers AV1 as their main codec. That was a big surprise, at least for me, because I always thought if we start seeing AV1 support in production, in product, you need to wait until the end of 2025 until you see something that makes sense.
Yeah.
Yes, demos, the ability to support that, just striking a feature. We do VP9, that's our suggested codec for you, but if you really want AV1, it's there, just enable that and don't come back if something gets wrong. Okay, things like that. But here, Jitsi came and said, this is what we support, period, out of the box. This is what we have. And then the most fascinating thing is that the whole post explains what have they done in order to get there. And that includes checking the CPU requirements and the memory requirements, understanding where can they run it and where it won't work and break down in terms of the specification of the device that is running the codecs. Then making sure that the payload types, the payload headers work the way they should. Adding all of the stuff that is needed on signaling to support that. Adding all the stuff that is needed on the RTP side to support that, because they did some things that are different than what we do in other video codecs. Support for SVC. They needed to add that as well. And then there was this minor problem that even if you do all that, with some devices, they're not going to be able to do AV1 because it's too CPU intensive. So they had to be able to say, well, We now have AV1, but we had in the past VP8 and VP9. We need to support them as well. So some calls are going to be on VP8 and VP9, although our preference is AV1, which is again great, but you need to be able to do it dynamically in the session. So it's like the two of us are doing this conversation. We have good machines. I don't, but never mind that. So we run AV1 for this call. A third person joins, he can't use AV1. What happens? At that moment in time, we need to downgrade all three of us to use VP9 or VP8.
Yeah.
And if things improve or he leaves, we need to know that and move back to AV1. So all that dynamic changes of the codecs are things that they've introduced to Jitsi in order to support AV1 as their preferred codec. Okay.
So Jitsi's made a big investment in the future, but because they're a big bet on the future here, but because we do have more industry alignment around AV1 being encoding of the future,
yes,
it's a safe bet, but they're still making it early, and so kudos to them for that, for making that investment in the application. But it sounds like it's primarily going to benefit them, or their users rather, in like smaller one-on-one calls between higher end users, and a tool like Jitsi Meet that does support multi-party conversations is less benefit in that multi-party, right?
I don't know, to tell you the truth, because in multi-party you decode more than you encode. And in multi-party, a lot of the users are going to be in very small windows, which means that you need to encode very little and decode very little in terms of bit rates.
That's true, yeah.
So then using AV1 might be the better approach. So I just don't know. I'm assuming, and I heard in a way, that a considerable percentage of their calls is actually using AV1 today already.
That's great.
So it's not as if it was only an investment in the future, it was an investment in the present.
Yeah.
But in a way that is very hard for others to come and compete. Okay? If you take Jitsi as an open source framework and say, well, can the other open source vendors do the same? Probably not that easily. Why is that? Because MediaSoup and Pion and Janus, okay, their client SDKs are not as sophisticated as the one that Jitsi has. Jitsi is a full-fledged application, so they can do all of these optimizations and bake that into the application. I don't see that happening inside the Janus or MediaSoup, because that's more akin to a server and you bring your client from home.
Right.
So they would have to invest a lot more on the client side than they have to achieve in any other solution that they have today. For example, if you look at the vendors that are doing today video, programmable video and video APIs and CPaaS stuff, and now they say, well, let's add AV1. That's great, but the market and industry is in the LLM side and generative AI, which we've discussed like a gazillion of times. Every month we talk about LLMs.
We almost got through this conversation without mentioning them.
Just try that last few seconds, cut it out, and then we continue. So they're going to be hard-pressed going back and saying, well, let's stop everything. We now need to find a video expert and start to explore that and do things here.
Right.
So in a way, I think it was a smart move from Jitsi part of doing that. And now they should go and invest in that thing that we should not be speaking about in this session, because it's important for everyone as well.
Right. All right. Well, it'll definitely be interesting to see more about, whatever statistics they share in the future about usage of AV1. But interesting and positive architectural change and positive sign for the adoption of AV1 in general. And as devices continue to catch up with it, we'll no doubt see wider spread usage of it across platforms too.
Definitely.
Well, Sahi, thanks as always for sharing your insights with us today. Anything else you want to add on this topic before we close?
No, I also mentioned that in my my tip of the that I send over my newsletter in Blog Geek Me. You can go subscribe and read these things there as well.
Perfect. All right. So as always, go check out bloggeek.me for more information about Sahi's work and for more information about future episodes of WebRTC Live. Check us out at WebRTC.ventures. Thanks, Sahi.
Thank you, Arin.
Thanks for joining us for WebRTC Live. Visit our website at WebRTC.Ventures to learn more about our custom design and development services and to learn more about upcoming episodes of WebRTC Live.